into RIT, SIS, I don't know what.
Okay. I'll put you present, no problem.
All right, thank you, Professor.
Okay. So guys, this is basically the next chapter, which is chapter number 10, in continuation to chapter number 9, phase diagrams. So I will talk about one of the major issue that you have in the phase diagrams, that it doesn't take time into consideration. Like for example, if you remember, do you remember this austenite going into the cementite and ferrite region? Do you remember this? It was like, if I remember, there was this alpha region was there, then there was this small triangular region, and gamma was here. So when gamma goes down, it cools down from eutectoid point, it happens, right? It have cementite and it have this ferrite basically in the laminar region. Do you guys remember this part, this reaction on the phase diagram? Yes. Do you remember? This is what I'm saying. So do you remember this eutectoid reaction where gamma goes into two phases in the laminar format, right? So I am going to show you basically, this is the one. This is the reaction that is happening in between. Gamma phase is going into these cementite and ferrite phases. But students, like there is one important question that's here, that what would happen if you are going to cool this thing slowly, like if the gamma is coming slowly or getting cooled down slowly and giving you this thing, or what about if gamma cools very fast, right? So in phase diagram, you do not know anything about time. Time is absent in this one. You only see the composition and you only see the temperature. You don't see how much time is present there. Because in steel, the problem is that the way it cools, it changes everything. Even the same reaction, which is here, eutectoid composition, when it is taken with respect to time, you will start getting different outputs. So this is where the phase transformation curve will come in play. Okay. Phase transformation, for example, phase alpha is going to transform into phase beta, or gamma is going into, for example, alpha plus cementite. There are two types, there are two major types of these phase. This is phase transformation, that one phase is going into different phases, right? Here alpha is going into beta, gamma is going into two different phases. So this phase transformation can be accomplished through two ways. One is through diffusive motion, where you know that atoms can move from one place to another place, right? And as a result of this atomic motion, what would happen? You will start getting a different phase, right? This is what happens, for example, when gamma cools into alpha plus cementite. So you remember that I told you that carbon atom readjusted, and they basically start giving you the cementite, which has more carbon than the alpha region, which has less carbon. So this is called diffusive. This is coming from the diffusion, right? Chapter number 5, atomic movement. Then there is another type of phase transformation that is called as displacive. And displacive is that there is no diffusion, but because of some pressure, because of some applied force, the atoms will suddenly change their position from one place to another place, right? Or suddenly change the atomic structure, the crystalline structure. So they will suddenly change, for example, from FCC to BCC, right? So there are two types of phase transformation. The phase transformation could be through diffusion because of the atomic movement, and it could be displacive, diffusive or displacive, where there is no change in atomic motion. The only thing is that there would be, because of the application of some force or something like that, some external force, they suddenly change their position or they suddenly shift their crystalline structure. So these are the two major things. This phase transformation, for example, the development of microstructure in both single and two-phase alloys ordinarily involves some type of phase transformation. So when austenite is going to do these two different phases, right, there are a number of phases which happens there. And technically, if I show you, you remember these eutectic point, this is the same old slide that we have used in the previous chapter as well. So this is the same, your tectoid point, your tectic point, and it's telling you, it's giving you Pearlite. Phase transformation, guys, when, for example, gamma is going into this one, it starts from the nucleation. You remember nucleation, right? So for example, when you have gamma here and gamma is going to change into alpha, you know that, you remember that we said that there would be in the hypo region, some particles will appear, alpha particles will appear. So that starting phase is called nucleation. When the new phase starts to come, that has started from the nucleation phase. So the first process to accompany the phase change, when one is changing into another one, for example, here this is going into alpha, it will start from the nucleation at different points. So what is nucleation? A formation of very small particle that is called as nuclei, right, of a new phase, which are capable of growing. So with the passage of time, what would happen? This nuclei will grow and it will start giving you a different phase, right? Favorable positions are the imperfection sites, where you have the problems, where you have the drawbacks. These are the potential sites, right? Where you have dislocations, where you have vacancy, or where you have, for example, some other types of defects. This is where it will start. So the initial phase is nucleation. Then the second stage of phase transformation is called as growth. So nuclei starts increasing in size, and that is basically called as growth. The transformation reaches completion if growth of these new phase particles are allowed to proceed until the equilibrium fraction is attained. So till you reach the equilibrium, these nuclei will grow, and eventually it will start giving you a new phase. Okay, so that's something which is there. Students, are you able to understand what I just said so far? Any question related to the phase transformation if you didn't understand anything so far? Yes, students. Guys, Saf, Amir, Yusuf.
Yes, Professor, it's clear.
Things are clear so far? Okay.
Yes, sir.
The next thing is that what is meant by kinetics? So kinetic is basically the study of the reaction rate of that phase transformation. If I want to see that phase transformation, for example, from gamma to alpha, is this a fast reaction or is this a slow reaction, or how much time is included? When I want to take it as a function of time, what would happen? It would be studied under this branch that's called as kinetics. So kinetic is nothing, it's just the study of reaction rates of phase transformations. Okay, and this is generally studied under the kinetics. If you want to look the diagram, or if you want to look basically or study the phase transformation with respect to the time, this is how the graph looks like. So on this side, for example, you have, let's say, pure alpha. This is pure 100% alpha phase. And on the other side, you have pure beta phase, right? So what does that mean? That alpha is going to change into beta. This is the complete phase change. You know that first nucleation will start. So with respect to time, you have time on x-axis and you have percentage fraction on the y-axis. So if you see, you will see that when alpha is going to change into beta phase, this starting period is where it will, this much time is taken basically to have a nucleation started. So you have these small dots which are coming, the first nuclei are forming at different locations. And after some time, when nucleation has been completed, then it will go towards the growth period. So growth is going to start from here now. If I change color, for example, here, put a blue color, this is where it's going to start, right? So you can see this thing now, alpha starts going to change into beta phase, right? And students, what would happen when it will reach in this time, when it will reach the other side? It means in this time, the whole alpha is changed into beta, right? So this is basically, if you are having a fixed temperature difference, this is how it would look like, right? If you fix the temperature, for example, this is what's going to see. Time is on this side. Students, when nucleation starts, you can see this thing. Initially, the rate is what? Rate is the slope. The rate is less, then suddenly rate is picking up, right? Like here, the slopes are changing. And then after some time slope starts to decrease again, right? So where the highest rate is present, if somebody asks you where the highest slope of the curve is present in this diagram, where the slope is highest.
The middle of the graph, sir.
The middle of the curve, right? So this is where the highest rate is achieved. So based on this thing, we say that I will talk about this thing, that why rate will go higher in the middle, like why what happens, but it is technically represented in this form. So if you see, for example, this time is telling you that around 50% of conversion has been performed. So if this is pure alpha and going to change into beta, when you take this thing in the middle, which means that students, I have a call coming from hospital. Just give me a minute. It's very important one. Okay. Sorry, students, that was an important call from the hospital that I need to pick. Hello, students, are you there?
Yes, sir.
Okay,
Yes,
so
Professor.
so I was telling that how do we calculate the rate? The rate is basically that if you see how much time is needed to achieve that 50% conversion from alpha to beta, that is called as rate, right? If you take inverse of that time, that is called as rate, right? So this is the definition of rate. And how do you specify this behavior? It is from this curve, from this equation that is called as Avrami's equation, where y is basically that how much fraction of percentage or how much fraction of alpha is, let's say, is transformed into beta. And K and N are basically, these are the transformation specific parameters. It depends on the different, what you can say, the transformation one, where T is basically the time that is involved, right? So this equation kind of depicts this behavior under the name called Avrami's equation. Students, one thing that is important, the rate here is less, but as you progress ahead, the rate will starts to go up. It's less slope, but slope is increasing, the rate is increasing. Maximum rate is in the middle, and then again it starts to decrease. So when nuclei are there, they starts to grow, you know, like nuclei are small dots, they starts to grow, right? So when they starts to grow, the rate initially is less, but then as they starts to grow, what would happen? Their area, their surface area will increase. So they have more capability to to grow faster. So that's why this growth rate will increase in the middle, the rate will increase in the middle, and then again when they starts getting bigger, and then near the completion, near the transformation, near the completion of transformation, the rate starts to go a bit less because there is not enough material that needs to be transformed. So this is like the generic, you can say, behavior of the transformation curve. Whenever one phase is going to change into different phase, this will give you this signature. It will give you this thing. Now that could be, for example, like this, that could be like this, that could be more like this, depends on that what are the conditions, what are the temperature, depends on this temperature, right? That I will show you in the coming slide. For example, if you try to see here I am going to show you that, for example, this is showing you the phase transformation, right? You have one phase, let's say alpha phase is here, and it's going to change into beta phase here. So here you see that with respect to different temperatures, you are going to see different curves, right? And on this axis, you have time. So you have this many minutes, 10 raised to power 4 minutes, like 10,000 minutes. This is 10 raised to power 2, let's 100 minutes. This is 10 minutes, this is 1 minute. So guys, which phase transformation is faster and which phase transformation is slower? What do you understand out of it? Yes. If you take these different scenarios, which one is faster transformation and which one is lower transformation, slower transformation?
I think the faster one is last graph.
Which one, 43 or 135?
43.
No, I think 135 is faster because it has a more vertical slope.
It has more vertical slopes. Also see the time. The time is mentioned here, right? So it started here, let's say around 2 minutes or 3 minutes, and it's going to end here, which is around 10 or 12 minutes. So this is faster. This is a time scale, right? So it started at this 2 minutes, and then the total completion happened, let's say in 12 minutes, right? Or 20 minutes or something like that. So this started faster and it finished faster. However, this started, for example, somewhere when you are around, let's say 9,000 minutes, and then it's going to complete even, it takes longer. What is this temperature? So this temperature is basically a kind of the temperature difference, or it's kind of basically that the rate increases with increasing temperature. So you can see this thing, that the rate will become faster if you start to make this temperature faster, going towards this thing, it is going to complete faster, start faster and finish faster. Yes, Yusuf.
Professor, this is all the same material, correct? All six of
Same
these slopes
material,
are the
same
same
material,
material,
yes.
but different temperatures.
Yes, same material with different temperatures. Yes. Yes. Right. I give you one example. So you guys remember, let me give you the example of, let's say you have a molten steel, molten metal that has temperature of 1000 degrees C. You bring it out of furnace and the room temperature is 20 degrees C, right? Would it cool faster or would it cool down slowly if the temperature gradient is that big? I give you two scenarios. Let's say this is one scenario. The other scenario is that you again pick the material out of 1000 degrees C, and let's say the temperature that you want to achieve is 900 degrees C. So delta T here is 100, delta T here, temperature difference is 920 here. Which one will reject heat faster? Yes. Which one will reject heat faster? The one that is cooling from 1000 to 20 degrees C, the one that is changing from 1000 to 900 degrees C. The final state is this one. Students, have you observed this thing? When you have 1000 degrees C, and let's say you put that metal in cold water that has a temperature minus 20 degrees C, what would happen? The cooling action is fast or slow? Yes, I am expecting answers.
It's faster.
Faster, right? So based on the temperature, that is delta T, that is basically the rate at which the heat transfer is happening, right? And if this rate is faster, so transformation is faster as well, right? It will cool down, it will become solid very quickly if it's a molten form. However, if it is in the same temperature range, delta T becomes smaller, then technically what would happen, that rejection rate of heat rejection or the time involved will become more. It will become slower. So that's the concept with respect to delta T you need to keep in mind. Here I am going to show you the same concept, that delta T is there, right? It is going to cool from gamma and it's going to cool below like this, right? So when it is going to cool below like this concept is called as undercooling, right? And when so gamma will starts to change, will start to change in these two phases when you cross this temperature boundary, right? When you cross this 727, so the moment it goes below 727, it starts to change into the to these ones. This is called basically undercooling. And one important thing, guys, you need to understand here. Now, when it is cooling down from 727, right, it can cool very fast. It can come to, for example, 200, 300 very quickly, or it can cool down slowly as well, right? It can cool down maybe slowly with less time, but that is dependent on delta T. If the delta T is smaller, then it would be a slower process. If the delta T is huge, then the cooling rate is faster. So I need to consider, for example, the cooling rate or delta T involved now at this stage, right? And students, now this thing is very logical, what I'm going to say. Think logically and think about this one. So for example, here I am going to show you when it is going to change from 727, this is where austenite is present. It's going to cool down, and let's suppose it's going to give you alpha plus this one, but delta T temperature is here by 675. So I am going to cool down from 727 to some point here. This is 720, so not 727, this is, for example, 675. This is 675. So how much would be delta T in this case? If it is going to cool down from 727 and I am going to stop at 675, how much is delta T? Yes. How much is delta T? 727 minus 675. What would be delta T, guys, in this case? 52?
52, Professor.
Right? In this case, 52 is the temperature difference. And another case, I cool it down quickly to 600. So if I cool it down to 600, how much is delta T for this case?
127.
127. So delta T for this one is 600 case is 127. And for the other case, it's 52. So if I try to plot, where do you see these two different temperature ranges? Where you have more temperature, would it be on this side or on this side? Like 120 C, 27 degree temperature.
127 will be on the left side, and the 52 will be more to the right side.
That's true. So this temperature range is technically delta T. That is making the process slower, or that is making the process faster. So if you have 52 delta T temperature, it means it will be on this side, towards the right side. If you increase the temperature range, the difference gradient, it will start going towards this side and it will complete faster. So this alpha going into this through things, it will be faster if you have this delta T, or it would be slower if you have this delta T, right? That's what I'm going to show you in the next picture. So if you go here, I will discuss what is this in a bit. But for example, see, where you have 600, delta T is larger, 127. See, it is going to be here. Where you have the temperature difference, for example, 675, delta T is smaller, so it will take more time. It is basically on the right side. Now, students, what's the influence of time on diffusion? Do you remember when we, like, how the transformation happens is through diffusion, right? I told you that gamma converts into alpha and this one. You remember these layers I told you, and I told you that carbon atom is going from gamma, that is a lot of carbon, that carbon content is going towards these smaller lines, which is basically for cementite, right? So for austenite, carbon starts to go into that one, making the layer of cementite, and alpha is less carbon content region. So these lines are basically coming because carbon is diffusing into it, right? Is readjusting. Now, can you link this thing? If you have more time, what would happen to the carbon? If you give more time for carbon diffusion, or if you give less time? Because we know that this is faster, we know this is slower process. So it will affect the diffusion process, the carbon readjustment. So students, what do you think? Where you will see more carbon? What would be the effect of that more carbon? If this is faster and it is the diffusion that is happening, you understand that in this case, if it's a faster process, there is not enough time given to the carbon atoms for the readjustment, right? It makes sense, right? When the process is faster, then the readjustment time for carbon is not there, because this happened very fast. And if I try to go for the slower, then diffusion is a time dependent phenomenon. So now it has more time where carbon can easily accumulate and easily transform from one place to another one. So what difference you see here? You see that these lines are thinner. These lines where you have cementite are thinner basically, in case where it is happening fast. And where you are giving more time, these lines will become thick inside, these cementite lines, right? So the influence of time will appear on what? On the layers of the cementite which is present. This is what I have written. With decreasing temperature, right, the carbon diffusion rate decreases. So if you starts going here, for example, right, when you starts to decrease temperature, delta T becomes larger. So as a result, the process is faster and diffusion rate decreases and the layer becomes progressively thinner. This is what you have seen here, for example, in this case. These layers will become thin because you're not giving enough time for the readjustment of carbon. Whereas if you go for the upper temperature, which means the smaller delta T, which means that now the process is slower, so enough time is provided for the diffusion and these layers will become thick, sorry. This will become thick. Here they are thinner. So what we say, where you have thick lines, we call this one coarse pearlite. Now there are two types coming out of pearlite. In phase diagram, we just understood one. That was pearlite, but now based on the time, we understand if it's faster or slower, we can get coarse pearlite or we can get fine pearlite. Right? This one is relatively soft. This one is relatively hard. Did it make sense to you guys? The explanation I just did? Yes. Yes, students.
Yes. Yes, sir.
Anyone want to quickly tell me again what I just said? Don't worry about the words. Like, can you describe the same concept what I just said in your own words? That how the faster and the slower will give you these two different scenarios. Yes, Samreed, you want to go and briefly talk about this one, just to make sure that you understand the concept?
So basically you said that the rate of diffusion varies. So
Okay. Okay.
the rate of the 675 degrees, the delta T is gives you coarse pearlite, and the fine pearlite comes from the higher.
That's true. That's true. That's very true. Always link this thing with the time, because this is slow. So slow means that you are giving more time for diffusion, right? Which gives a coarse, like more thicker lines for the cementite. For the faster one, you don't give enough time. So these lines are thinner basically, right? So yes, that's true. That's what you have seen here. Another way to represent this phase transformation is this diagram. So this diagram is called as time